Hello students, welcome to my lecture series on reinforced concrete structures. In this class, I am going to discuss about design of singly reinforced beams. The outcomes of today's lecture are, on completion of this class, you will be able to know what are the codal recommendations for design of singly reinforced rectangular beams. And also you should know what are the design steps to be followed for a design of singly reinforced rectangular beams. So let us recall what are the things we had discussed in last class. We had discussed about limiting depth of neutral axis and limiting moment of resistance. So what do you mean by this limiting depth of neutral axis? So this neutral axis can be obtained when concrete and steel reaches their maximum permissible strains at the same time. That means yielding of concrete and yielding of strains will starts at the same time and ends at the same time. The depth what we obtain from this phenomenon is called limiting depth of neutral axis. This also called it as a maximum depth of neutral axis. This can be obtained by the formula. This formula we have obtained from similar triangle of strain diagram. The final formula of calculating XU max, that is limiting depth of neutral axis, is XU max by D is equal to 0.0035 by 0.87 Fy by Es plus 0.0055. Here, for given depth of the beam, if you substitute grade of steel, then you can calculate what is the limiting depth of the neutral axis or the maximum depth of neutral axis. So as we discussed that XU max, that means limiting depth of neutral axis, only depends on grade of steel. It will not depend upon any other factors like what type of loading we are applying on that, what is the grade of concrete we are using, and what are the cross-sectional dimensions of the member. That will not depend upon those parameters. It will depend only on grade of steel. Right. And we have also defined what are the different types of section based on their failure modes. These are basically three types. One is a balanced section, under reinforced section, over reinforced section. So what is the definition of a balanced section? Here the definition of balanced section is the steel reinforcement reaches the yield strain, that is 0.87 Fy by Es plus 0.002, and concrete reaches the maximum strain of 0.0035 at the same time. As we know these two values, this is the tensile strain, which should not be less than to this value in the member, and the maximum compressive strain in the RC member. And when these two strains, the strain in concrete and the strain in steel, attains their maximum value or the permissible value at the same time, then the section what you defined is a balanced section. Similarly, under reinforced section, here in under reinforced section, first steel will reach its maximum strain than concrete. So what will happen if steel reaches its maximum strain earlier than the concrete? So steel will fail first than the concrete. That means as steel is a ductile material, when it is fails first, it will give sufficient warning before failure. Right? And in this under reinforced section, the steel provided is less than that of balanced section. So the designer will prefer the under reinforced sections only. Because for what is the reason for this? The reason is the under reinforced sections are economical and safer. How it is economical? I defined in last class that we are using the steel reinforcement or any kind of reinforcement are less than the required for the balanced section. So we can reduce. We are reducing the amount of steel so that we can reducing the cost of that steel and labors or the manpower required for the steel bar bending. For that we are reducing that. So and one more, it is I also told you that it is safer. How it is safer? It is safer because before failure steel will give sufficient warning as it is a ductile material. So I can say it is a safer. Because of these two reasons, designer will prefer only under reinforced sections only. And we have another type of section, over reinforced section. Here in this, concrete will reach its strain first, maximum value of strain first than the steel. So here we can call it as a compression failure, means in this scenario the concrete will fail first than the steel. So as concrete is the brittle material, so it will not give any warning before failure of it. And whatever the steel provided in this over reinforced section, the amount of steel is more than that of the balanced section. So I can say this over reinforced section is unsafe and uneconomical. It is uneconomical because we are using the more steel than the balanced section. It is unsafe because it will not giving any warning before collapse of this. That means it is a brittle material, so it can suddenly collapse. That's why I can say it is unsafe and uneconomical. So designer will not suggest over reinforced section, and also our IS 456-2000 limit state method will not accept this over reinforced section also, right? And we have discussed one more thing, that is the limiting moment of resistance. So as we have the limiting depth of neutral axis, if we calculate the moment of resistance with respect to that particular axis, then we can call it as a limiting moment of resistance. Here the given definition is the moment of resistance corresponding to the XU max is called limiting moment of resistance. This is all we have discussed in last class. Now in today's class we will discuss about general requirements of a design requirements of a beams, right? So generally in this singly reinforced beams we will design simply supported beams and cantilever beams. So the first requirement is, as per codal provision, the effective span. What will be the effective span will for simply supported beam is, as per IS 456-2000 clause number 22.2, the effective span for simply supported beam is center to center of supports, and another condition is clear span plus effective depth. We have to choose a minimum of these two values as a effective span. So I will explain very clearly with the help of this sketch. Here I have a simply supported beam as it is supported over two simply supports, and we have a clear span. What is the definition of clear span here? Clear span nothing but the distance between the two inner faces of the support. So this is the inner face of the support and this is one more inner face of support. The distance between two is called, I can say, clear span. But we require what is the effective span is. So effective span can be calculated in two ways. One is center to center of support. That means the width of the support is B here, and we have another end support is B, and we have, if you take the center of the support to the center of the support, in this way we can calculate what is the center to center support, that is called a effective span. That effective span can be calculated, that is small l is here effective span, capital L that is a clear span plus half of width of one support and half width of another support, that will give the total effective length. And another formula also given as per our IS 456-2000, that is clear span plus effective depth. You know what is the definition of effective depth is? Effective depth nothing but it is a distance from topmost fiber of a compression zone to the centroid of a steel reinforcement. So this is the steel in the longitudinal section. We can see here the steel reinforcement provided here, and here the 3 number of bar provided. Those bars are behind this, so we cannot see in that longitudinal section. Those bars can be seen in cross section. So 1, 2, 3 they are provided. The effective depth is the outermost fiber of a compression zone to the centroid of a steel reinforcement. This is called effective depth. So as per this class number, what is the effective span is means for a simply supported beam, clear span, that is L plus D. L plus D. So this is another way of finding your effective span. So we can take, for our design purpose, we can take the minimum of these two value as a effective span. Is this clear, students? Right. Again, I will give the formula for this according to this figure. The center to center of support means, that is effective length L equal to clear span L plus B by 2 plus B by 2. That is this center to this center distance. And another equation is a clear span plus effective depth. Clear span is L and effective depth is here D. So I can write capital L plus D as the effective span. the minimum of these two values considered as a effective span for design of simply supported beam as per class number 22.2 of IS 456-2000. So this is the first criteria for a design requirements of a beam. And second one is for if you are designing a cantilever beam, then how we take the effective length of that particular beam. As we know that for a cantilever beam of a singly reinforced cantilever beam, we have to provide the reinforcement, the tension zone. The tension for this cantilever beam, tension zone will occur above the neutral axis, that is here, as the topmost fibers of the beam are subjected to tensile force when it is subjected to a vertical loading. So the cross section will be like this. According to the codal provision, that the length of the face of the support plus half the effective depth except where it forms the end of the continuous beam. It means, this I will explain with respect to this figure. If you are designing a cantilever beam as a singly reinforced cantilever beam, the effective length of that cantilever beam can be calculated using this statement. The meaning of this statement will be, that is the length of a beam from the side face, from the face of the support, plus half of the effective depth. So this is the effective depth of the cantilever beam, and this is center of the reinforcement to the bottom fiber of a compression zone for this cantilever beam. So effective length L equal to this L, that is length of the beam up to the face of the support to the half of your effective length, that is D by 2. Finally, I can calculate the effective length of a singly reinforced cantilever beam, that is small l equal to capital L plus D by 2. So this is how we can calculate effective length for simply supported beam as well as for a cantilever beam. So next criteria will be deflection control. So deflection, the vertical deflection limits may generally assumed to be satisfied provided that span to depth ratio are not greater than the value specified in the class number of IS 456-2000, that is 23.2.1. According to this class, the L by D ratio should not more than those values. Now see what are those values as per that code. Here two criteria is given, criteria A and criteria B. Here according to the first criteria, the basic value of span to effective depth ratio for the span up to the 10 meters. Just you have in first criteria they have consider the span of the beam is up to the 10 meters only. For a 10 meters span, if we consider cantilever beam, the span to effective depth ratio is equal to 7. If we consider simply supported beam, that L by, I can call it as a L by D. L is the effective span and small d is the effective depth. So L by D ratio for simply supported beam is 20, for continuous beam it is 26. These values are valid up to a beam's length of 10 meter. If beam length beyond this 10 meters, then how we calculate these basic values of L by D ratio? So there is a provision that in the code also, that is in the form of criteria B here, for a span above 10 meters, the above values that is given in A, criteria A, are to be multiplied by 10 by span length in meter. So I have given one example how to calculate these basic values for the spans beyond that, more than the 10 meters. Here say, let us take example, the span length is 12 meter for a simply supported beam, so which is greater than 10. And the L by D ratio can be calculated according to this, that actually up to 10 meters, that is the L by D ratio is 20, but as it is a beyond 10 meters, so that should be multiplied by the 10 by span here. So 20 multiplied by 10 by, what is the span length? 12 meters. If you calculate that, I will get 16.66 is the L by D ratio for a simply supported beam spanning 12 meters length. So this is how we calculate for the other conditions also when they are exceeding their spans 10 meters. Right. Now third criteria is, depending upon the percentage of tension reinforcement and stresses of steel for a tensile reinforcement values in criteria A and criteria B to be multiplied with a modification factor as shown in figure 1. That figure is a graph. Here, after calculating the basic value, those basic values are to be multiplied with a modification factor. How to get that modification factor? First of all, we have to calculate what is the steel stress of service load, Fs. Fs value we have to calculate. This Fs value can be calculated by using this codal formula, that is Fs equal to 0.58 Fy into area of cross section of steel required by area of cross section of steel provided. So in the graph, on y-axis we have a modification factor, and x-axis we have a percentage of tension reinforcement, and in between we have a various values of Fs, that is a service steel stress of service loads. That is simply say that is stress of steel under service loads. These are the graphs given for different values. For calculating that Fs value, for calculating percentage of tensile reinforcement, from that we can calculate what is the modification factor is. So let's say we want to calculate what is that the stress in steel under service load, that is Fs equal to 0.58 Fy. You know the Fy is the given that yield strength of the steel, and area of cross section of a steel required and area of cross section of steel provided. What do you mean by these two? What is the basic difference between these two? So let me define here. Area of cross section of a steel required means how much steel required for particular section, that is a required, and how much you are providing is nothing but a provided. How to differentiate these two means, say area of steel required, you are calculated area of steel required is say 500 mm square. If you calculate number of bars for that particular area of steel, say you are assuming say for 10 mm bars you are provided, for example I am saying 10 mm bars are provided, so 500 by area of 10 mm bar, so that is 78.5. If I divide that, we will get that value of that number of bars required is say 3.35. Will you provide the 3.35 bars in the RC member in the form of fraction? So we cannot provide, we can provide 3 or 4, we cannot provide in between number of bars 3.35, right? So we have to provide here, say we always go for higher end, so we will provide say 4 number of bars, right? Required is 3.35 bars, but we are providing 4 bars. So the area of cross section of steel required means the area of bars required, that is 3 point, area of steel corresponding to the number of bars required 3.35. That is the required, and provided is, are you providing 3.35 number of bars? No, we are providing 4 number of bars. So we have to calculate now what is the area of steel corresponding to the 4 number of 10 mm bars. That is called area of cross section of steel provided. I hope you are clear. Otherwise, we will discuss later when we are discussing the problems. Right. So we have calculated percentage of tension reinforcement, and according to this formula, we have calculated what is the steel stress of service load. Say if I get 0.8 percentage of tensile reinforcement, and I got 190 is the Fs in Newton per meter square. So if you have to calculate the modification factor for this particular values, so this is 0.8 on the x-axis, that is a percentage of tensile reinforcement. Now you go perpendicular to this x-axis and bisect this Fs 190 curve, and this horizontally project onto the y-axis. Say here your modification factor will be here in between 1.2 to 1.6. So I know that where it is where the modification factor will be, that is in the range of 1. I know that 1.2 to 1.5, 1.6. So the exact value can be calculated by using interpolation technique. There I will explain when we are discussing the problem. Then I will discuss about interpolation. By using interpolation technique, we can calculate what is the exact value of modification factor. Right. Now I have calculated modification factor. With this modification factor, I will multiply what is my earlier calculated basic value. Like that, we have to calculate L by D ratio again. Right. So this is in tension reinforcement. Similarly, we have to calculate in compression reinforcement also. Depending upon the area of compression reinforcement, the value of span to depth ratio shall further modified by multiplying with the modification factor given in the figure 2 in as per IS 456. This graph is given. So same, we have percentage of compression reinforcement in x-axis and modification factor on y-axis. So let's say, suppose we are getting the percentage of compression reinforcement is say 1%, the corresponding modification factor will be here, it is in between 1.2 to 1.3. For exact value of this modification factor, we will do the linear interpolation between 1.2 to 1.3. This is how we calculate the modification factor in compression reinforcement. So another requirement in design of singly reinforced beams are minimum tension reinforcement provided. Here, as per IS 456 class number 26.5.1.1, the minimum area of tension reinforcement shall not be less than this value. That is, AS by BD is equal to 0.85 by Fi. You know, area is minimum area of tension reinforcement. BD nothing but B is the width of the beam, D is the effective depth of the beam. Here Fi is the yield strength of steel. That is dependent upon what grade of concrete, what grade of steel we are providing, right? So according to this formula, we can calculate what is the minimum tension reinforcement. So this tension reinforcement should not be the provided tension reinforcement shall not be less than this AS value. So when we have the minimum tension reinforcement, so we have to calculate what maximum value of reinforcement we can provide in the beam. For that also, a code has given some provision that the maximum area of tension reinforcement shall not be exceed 0.04 into BD, or this can be written as 4% of gross cross sectional area. Here B is your width of the beam, and capital D is here gross depth of the beam. When you are calculating maximum area of tension reinforcement, you should use the gross depth of the beam instead of effective depth of the beam. So the area of reinforcement what we calculated in this reinforced beam, that should not be exceed 4% of gross sectional area. So these are very important for your dear students. Remember that these values what I discussed so far, those values are very important for your competitive exams. Straight away we will get the question like, what is the maximum area of tension reinforcement should not exceed, that is 4%, 5%, 6% of gross sectional area. Like that you will give the option. So you have to tick on, it should not exceed 4% of gross cross sectional area. Sometimes he may give, instead of gross, he will give that effective area. He may mention effective area. How we get the effective area? That is B multiplied by small d, like that. That is a wrong answer. We are calculating the maximum steel reinforcement provided in the beam with respect to the gross cross sectional area of a beam. Right. Next, side face reinforcement will be provided when we have to provide the side face reinforcement. Shall we provide either face of the beam or only one face? If you provide either face of the beam, how much you have to provide? Those things we discuss here. As per class number 26.5.1.3 of IS 456-2000, there are some recommendation given for side face reinforcement. So it will be provided when depth of the beam exceeds 750 mm. Then only we can provide side face reinforcement. It should be provided both sides of the beam, both side faces of the beam. That is, it should be provided along the two faces. The total area of reinforcement shall not be less than 0.1% of web area. So if you take a T-beam, we have a web portion, and the web portion if exceeds 750 mm, then we go for a side face reinforcement. For that, the amount of steel required that should not be less than 0.1% of that particular web area. And what is the spacing should be provided for this? It shall be distributed equally on two faces at spacing not exceeding 300 mm or web thickness, whichever less. The side face reinforcement spacing should not exceed 3 mm, or another case it should not it is equal to thickness of web. Among these three values, we have to provide lesser value as a spacing of side face reinforcement. And next we have a cover to the reinforcement. What do you mean by cover? This thing also we have discussed earlier in our previous topics. Cover, effective cover or clear cover. Cover nothing but just simply a clear cover. It is simply, we can define it. It is a distance between the bottom of the reinforcement to the bottom of the beam. Or if you want to define what is effective cover means, it is centroid of the steel reinforcement to the bottom of the beam. So we can define like this: simple clear cover and effective cover. And why should we provide this cover in the reinforced members? It should be provided in the member to protect the reinforcement against corrosion and fire. Suppose if you not provided a cover in the member, then the reinforcement will expose to the atmosphere. Because of some atmospheric weathering action, it may corrode, or if any fire accident taking place, the steel reinforcement also catches the fire. To avoid those things, we have to provide some cover based on their exposure conditions. As IS 456-2000 specifies the following covers to be meet durability requirement as shown in below table. As based on the cover given based on their exposure conditions. The exposure condition I have already discussed in my previous lectures, like when we are discussing about the properties of concrete. I have discussed what is the definition of mild exposure, moderate exposure, severe exposure, very severe exposure, and extreme exposure conditions. Say if you are doing concrete in mild exposure condition, or you are constructing beam in mild exposure condition, then the nominal cover of a concrete should not be less than 20 mm. You are doing concreting in moderate condition, then it should not be less than 30 mm. In severe condition, it should not be less than 40 mm, 45 mm. And very severe conditions, it should not be less than 50 mm. And very extreme conditions, then it should not be less than 75 mm. This nominal cover should be used for this particular exposure condition of usage of concrete. Right. Next, spacing of reinforcement bar. Yeah, we have designed main bars and distribution bars, everything for in the beam. Then how to provide, how much spacing we have to use for that bars. Here we have two criteria, that is one for horizontal spacing, another is vertical spacing. Sometimes we have provide vertical reinforcement also, then how much will be the vertical reinforcement spacing should be provided. So let's discuss the horizontal. First criteria, the horizontal distance between two parallel main bar shall not be less than the greatest of the following. That means maximum of the following. One is diameter of bar, if the bars of the same diameter. A second condition is diameter of larger bar if the diameter are unequal. Say these bars are provided the main reinforcement in the beam, and these are the horizontal bar. I am showing the cross section here, cross section of a beam. This the horizontal distance between two parallel, these are the two parallel bars. The value must be greater of the following. Say when these two bar of same diameter used, one condition. If this and among these three bars, which bar has a maximum diameter, the spacing should be provided according to that maximum diameter of bar. So that is the first criteria. And second criteria is B. When the bars are in row, that means you are providing like this, 1, 2, 3 like this, should be vertical in line. Okay, the cross section will be vertical in line. The minimum distance between the bars shall not be greater than the following values. So the spacing between these two vertically spaced bars are greater of the following values. One is 15 mm, second one is 2/3 of nominal size of the aggregate, and third one is maximum diameter of bar. Among these three values, which will we get the maximum value? That value provided as a when the bars are provided in row for a beam. Next, this is all about the design requirements of a reinforced beams. Then we have a design procedure for singly reinforced beam. Now we see the step-by-step procedure for designing the reinforced beam. The first step will be calculate the overall depth of the beam. So here before this we have to calculate what is the effective depth of the beam. What is the effective length of the beam. Sometimes directly in the problem directly will give the effective length of the beam. If not, in the problem is not mentioned the effective length of the beam. If it gives only clear span or clear span of the beam, then we have to calculate the effective length of the beam. You know, already we have discussed our very beginning of this topic, that is how to calculate effective length of a simply supported beam and the cantilever beam is. So that is, we have some criteria. Based on those criteria, we have to calculate effective length of the beam if the effective length of the beam is not given in our problem. If given in the problem, you have to start from this step. So the first step will be calculate the overall depth. By assuming, this can be calculated by assuming overall depth of the beam is equal to effective length by 12 to effective length by 15. Between these two range, we have to choose. So L already we have given that L by 12 to L by 50. Among these two values, you can choose any one of in between these two values and calculate what is the overall depth of the beam. Once you know the overall depth of the beam, you have to calculate what is the width of the beam is in second step. Generally, width of the beam will be small b, that is half of d to 1/3 of d. Here d is overall, so capital D is overall depth. Right? Between these two values, we can choose what is your width of the beam. In step 3, calculate the effective width of the beam. This is step 3. Effective width of the beam. Effective depth of, it is not effective width, sorry again. Effective depth of the beam. Effective depth of the beam can be calculated, small d is equal to d minus a cover. If cover is mentioned in the problem, that's okay. Cover is not mentioned in the problem, you have to choose suitable cover as provided in your previous tables. That is for mild exposure condition, what is that? And severe exposure condition, what is that? There are some values are there. From the table, you have to choose what is the cover is. From that, you can calculate what is the effective depth of the beam. Dear students, please make it correct. It is not the effective width of the beam, it is the effective depth of the beam in third step. Right. In the fourth step, you have to calculate a load. So this is a very, very important and crucial step. Based on the load only, we have to design the cross section of a member. As we know, design nothing but determine the cross sections and amount of steel reinforcement required for the particular section. So it is a very crucial step. So design load calculation can be calculated based on dead loads and live loads. If any other loads are given, like what is the finishes loads, those also included in this, but I included only dead load, that is nothing but a self-weight of the beam, that can be calculated, the width of the beam multiplied by overall depth multiplied by unit weight of RCC, that will come in kilonewton per meter. As we know that unit weight of RCC is 25 kilonewton per meter cube, and this B and D, this B can be obtained by your second step, D can be obtained by your first step. Those values, if you multiply, will get what is the dead load is. And live load is certainly mentioned in the problem, definitely. Otherwise, we can take for particular case what is the live load is according to IS 875 part 2. From that we can consider. Definitely for your university exams or your board exams, you will mention definitely what is the live load is. Now we have to calculate total load. Total load nothing but what are the different loads sum of what are the different loads acting on that beam. So I am assuming here only two loads are acting, one is dead load and live load. Sum of these two loads, dead load and live load, is called it as a total load. Right. As we discussed, when you discuss design philosophy of a limit state method, and when you are discussing importance of partial factor of safety, the partial factor of safety can be used to enhance the design load. So this is the actual load, that is dead load plus live load, that can be enhanced by multiplying with a 1.5. What is the 1.5 here? We know as per limit state of collapse in flexure condition, when we use a combination of dead load plus live load, then you can use the partial safety factor is 1.5. So the obtained total load can be multiplied with a 1.5, then we get factor load or factored design load, that is WU. According to this, we can calculate what are the dimensions of the RC member and amount of steel reinforcement required. So the factor load W nothing but 1.5 times total load. Next, calculation of step number 5, we have a calculation of design moments. Suppose if you are designing for simply supported beam, then simply supported beam subjected to UDL, then what is the maximum bending moment we get? That will be the design bending moment. So that is mu equal to WU L square by 8. We are using here factor load, and so it is, I can say, factored bending moment also. For WL, generally it will be WL square by 8 for when you simply supported beam subjected to UDL, but we are using a design factored design load, so we can calculate what is the factored bending moment is. Factored bending moment will be m equal to WU L square by 8. This is for simply supported beam. When a cantilever beam subjected to uniformly distributed load, then the factored bending moment can be calculated by WU L square by 2. This formula you can obtain by your strength of material topic when we are calculating bending moment calculation for different condition of loading. Right. Next, when you are calculating that is the factored bending moment, and we also need to calculate what is the limiting moment of resistance of a particular beam. When you know the actual depth of neutral axis and when you know everything, then we can calculate what is the limiting moment of resistance. You know what is the definition of limiting moment of resistance is? Moment of resistance calculated with respect to the limiting depth of neutral axis. By calculating, the purpose of calculating this limiting moment of resistance is to decide the type of section. Then when we are analyzing the beam, we have decided the type of beam based on the actual depth of neutral axis and the limiting depth of neutral axis. Based on that, we have to calculate limiting moment of resistance and the factored bending moment. If the factored bending moment is equal to the limiting moment of resistance, then that beam is termed as balanced section, or that the section of a beam is termed as balanced section. Similarly, if the factored bending moment is less than limiting moment of resistance is that this section comes under reinforced section. Finally, if the factored bending moment is greater than limiting moment of resistance, this is defined as a over reinforced section. We know that ready-made formulas for calculating limiting moment of resistance for different grade of steel, that is as per IS 456-2000, limiting moment of resistance can be calculated from below the following table. If you are using Fe250 grade of steel, then this will be the formula, that is 0.148 FCK BD square. Here if you are using Fe415 steel, that the limiting moment of resistance can be calculated by using 0.138 FCK BD square, and if you are using Fe500 steel, that limiting moment of resistance can be calculated by using 0.133 FCK BD square. Right. Now we have calculated factored bending moment and moment of resistance. What is the maximum moment of resistance of a particular beam for given assumed depth and width of the beam? And also because of load, factored load, we have calculated what is the factored bending moment comes. So when your beam setup is stable, those two should be equal. That is, factored bending moment must be equal to the moment of resistance developed in the particular RC beam. So this can be calculated ME equal to MU limit. Here MU limit can be, it is not root, sorry, discard this. MU is equal to K into FCK BD square. Here K is nothing but it is a factor that is depends upon your grade of steel. So if you use Fe250, simply that this K value you can obtain from that formula, 0.148, and Fe415 it is 0.138 and Fe250 0.138. And required depth can be calculated from this formula, that is small d equal to under root of, that is factored bending moment by K into FCK into B. The factored bending moment is already calculated in your previous step. K is depend upon the grade of steel. If you are using any grade of steel, corresponding K value you can substitute. FCK is a grade of concrete and B is already obtained from step number 2. From that you can calculate what is the required depth. Suppose here we have two depths. One is assumed depth and required depth. If your effective depth required is less than the provided, that means this calculated value, this required depth calculated value is less than our whatever we assumed, that is half of overall depth to the 1/3 of overall depth value. If that value is greater than this required depth, then we can provide that already assumed depth and we can go for further step. If it is less than that, we can provide, if this provided depth is less than the depth required, then we can provide depth required and we can proceed. Right. Finally, another step is the calculation of, our ultimate aim is to calculate dimensions and area of steel reinforcement. From this step we have calculated what is the D, and already we know B. According to BD, that means cross section we have calculated. Remaining thing we have to calculate is that area of steel. If you calculate that area of steel, your designing is over. Right. The next step will be calculation of area of steel reinforcement. This can be obtained from ultimate moment of resistance, that is MU. That MU is equal to, we can calculate with these two formulas. These two formulas can be this formula we can get from your IS 456-2000 code. That formula will be MU equal to 0.87 Fi AST D into 1 minus Fi AST by BD into FCK. So if you substitute all those values, MU value already we have calculated, Fi and D value and B value, FCK value. From this you can calculate what is the AST is. Here, if you use this formula and calculate AST, you will get a quadratic equation. We have to calculate, we have to solve that quadratic equation. For the quadratic equation, we get two factors, but you have to calculate with respect to positive factor of that, you have to calculate the area of steel. If it is a little tedious process, it will require more calculation. If you directly substitute the values, the parameter what we have with us, that is FCK, Fy, Mu and BD values in this formula, directly we can get AST value. So it is up to you, whichever is easy to you, your convenient, whichever is easy to you, you can calculate AST. But whatever the value you are getting for this and this, both are same. So don't confuse with these two. You can use this formula or this one. This is directly give the answer. This equation will form the quadratic equation. You know that for quadratic equation we will get two factors. From the positive factor we have to calculate, with respect to the positive factor, you have to calculate what is the AST is. It's simple. It is also simple, but it has some more calculations compared to this equation. Right. Now we have design is over. Now a design cross section of a beam and area of steel provided are really safe. Whether they are safe or not, we have to go for check. So first we have to check for minimum area of reinforcement. We know as per class number 26.5.1.1a of IS 456-2000, the minimum area of steel shall not be less than by given the following. That is AS by BD equal to 0.85 by Fy. The area which is calculated, area of steel which is calculated, that should not be less than area of this. So AST obtained should be greater than this AS, and otherwise you have to provide whatever the minimum value you got AS, that will be provided as a AST. That is the one class. And second one, we have to check for maximum area of reinforcement. According to the class number 26.5.1.1 of IS 456-2000, that the maximum area of tensile reinforcement shall not be exceed, that is 4% of gross cross-sectional area. The AST obtained should be less than that this gross cross-sectional area. If not, we have to go for revision of section. If you get more than this, we have to go again revision of section, so that we can get the AST less than 0.04 of gross cross-sectional area of the member. Next, spacing of the bar. So how to calculate spacing and how to calculate the number of bars here. So assume suitable diameter of bars and number of bars can be calculated. Estimated or calculated area of steel by area of one single bar. So for calculating number of bars, I have given one example here. So diameter of bar assumed is 10 mm. AST I have calculated from previous data is 500 mm square, and area of 10 mm bar is 78.5 mm square. I want to calculate, say, number of bars required. So that is 500 by 78.5. So I have got 6.35. I cannot provide this fractional form. I have to provide either 6 or above value. Generally, we go beyond this value, say 7 number of 10 mm bars should be provided. So we have got a number of bars required, and according to the codal provisions, we have to provide the spacing between these. We have already discussed in your design requirements, when you are discussing about design requirement for spacing. When you provide as a main bar in horizontal or vertical direction, what are the space requirement we have? Those requirements we have to use here. Next, last one, we have to check for deflection. So this is very important criteria for a design. So this can be checked with the help of our steel stress under service loads and percentage of steel, and finally by using those two values we have to calculate the modification factor, those graph available. Right here, the calculation of service stress Fs and percentage of steel we can calculate by AST by BD, area of cross section, multiplied by 100. From that you can calculate, and this Fs can be calculated as I already discussed, that is 0.58 Fy into AST required by AST provided. From this formula I can calculate. Sometime this formula can be written as Fs equal to 0.58 Fy also, where if your denominator value and numerator value one and the same, then we will get cancelled. Finally, we use Fs equal to 0.58 Fy. As your AST required is AST provided, then it will get cancelled. Then final formula will be remains with Fs equal to 0.58 Fy. Right. By using these two values, we can find out what is the modification factor. To find out the modification factor, KT. Say assume here the KT is the modification factor for me, and Fs and PT values from figure. I have copied from some of the textbook. That is a figure number. According to our lecture, that is table figure number 1 and figure number 2. Figure number 1 is for tension reinforcement. Figure number 2 is for compression reinforcement. So as we are designing a single reinforcement beam, we are providing a reinforcement tension. We have to see only tension reinforcement, that modification factor figure only. Here the L by D maximum equal to, for a simply supported beam discussing, L by D maximum is equal to 20 times the modification factor. As we know, the basic value for length to the depth, effective depth ratio is 20 for that simply supported beam. If you multiply that basic value with your modification factor, you will get a new value. And second, for the cantilever beams, there is L by D maximum equal to 7 times the modification factor. As we know that length to effective depth ratio for cantilever beam is 7. Right. If the L by D maximum is greater than L by D provided, hence our member is safe against the deflection. So we can say hence it is working. If your L by D maximum is less than L by D provided, then we go for redesign of the section. So what do you mean by this? L by D maximum is, we can calculate it from this. L by D maximum for simply supported beam, we can use calculate from this. What is L by D provided? Means L by D provided means how much we are providing this ratio. So here L means we have already calculated what is the effective length of the beam. Effective length of the beam, and that can be calculated by using codal provision that if you use simply supported beam, that is center to center distance between the support or the clear span plus half of the clear support plus effective depth of the beam. From these two conditions, minimum value we can consider as a effective length of the beam, and this small d is effective depth that we can calculate from step number 2. The ratio of these two is called a provided. This ratio should be greater than the maximum value for the codal provision. Then we can say our design is safe, otherwise it is unsafe. Right. Next we have as usual some competitive exam questions which are asked in previous exams like ECET and all. That the first question will be maximum area of tension reinforcement shall not be less than, that is 0.04 BD. This is for codal provision. As for IS 456-2000, the area should not exceed this 4% of BD, gross cross-sectional area. And the second question will be for cantilever beam, the value of L by D ratio for stiffness considered. Stiffness into a deflection consideration, that is generally 7. Just now we have discussed that. The option A is correct. The next question will be for a simply supported beam, the value of L by D ratio from the stiffness consideration, that is the deflection consideration, that will be 20 actually as per IS 456-2000. So option B is correct. The fourth question will be what is the value of nominal cover to meet a durability requirement for mild exposure condition? So for mild exposure condition, it is given in the table is, that is 20 mm. So option D is correct. It is given as per IS 456-2000 values. And the last question is what is the value of XU max by D for Fe 415 steel? This is again from codal provision. For this 0.48. So option B is correct. So these all the answer for all these question will get if you refer IS 456-2000. Remember the student, just note the student, while you are writing competitive examination, you will not allow to take any code books to the exam. When you are writing a semester or board examination, you are eligible to take the code book to the examination. So when you are writing competitive examination, you should remember the values what you mentioned in the codes. Not only for the RCC, you can use the code for design of steel structure also. There also you can remember some values for your competitive exam purpose. So that's all for today's lecture. Thank you.